Now, here's a really simple sounding question. Why don't spinning coins just fall over immediately? If you've ever flicked a coin across a table or spun one on its edge, you probably noticed something really weird. It doesn't just tip over right away. Instead, it stays upright, rolling or spinning for an unexpectedly long time, totally stabilized, before eventually wobbling and falling over. What is it about spinning that seems to stabilize an object? But coins aren't the only objects that behave this way. For instance, why do spinning tops stay balanced until they slow down? How does a bicycle remain stable when moving but it falls over right away when it's stationary? And what's really keeping a football spiraling smoothly through the air instead of tumbling over immediately? All of this boils down to two powerful concepts in physics: angular momentum and the moment of inertia. So, here today, I'd like to explore how these forces work together to create stability in objects that are spinning. I'd like to break it all down with high speed footage of spinning and rolling coins, and then dive into the science and the details behind this incredible effect. And by the end of all of this, I'd like you to not only understand why these objects behave the way that they do, but I'd like you to also understand that the same physics governs everything from satellites that are spinning when they're launched in space to figure skaters on ice. Let's go ahead and get started. So grab a few coins here, and I'll encourage you to just throw them and just watch them and see if you notice what's going on. When I drop these things, they obviously go every which direction, and they don't appear to be very stable. Let's do it again. As I just kind of like let them come out, I can see them bounce every which direction. Occasionally you can see one land on the edge and then bounce and then spin a little bit and then eventually tumble down and settle down into its final state. But in general, when you just drop coins, they are what we call not stable, right? So alternatively, I can take a coin and I can just kind of like drop it, and it might balance for a second, but obviously it's not stable. Now, the interesting thing about this is if I do something to this coin before I let it go, then it becomes more or less stable. Let me talk to you about what that is. So here, if I grab this coin here and then just give it a little bit of rotation like this, then suddenly it is stable just by adding a little bit of rotation. Now, I know what you're thinking. You're thinking, well, duh, we see that every day. But instead of just assuming, oh, that makes sense, that's normal, let's talk about why is that the case. It's because it's kind of weird. Now, I think what's really interesting about this is if you just give a little bit of rotational motion, then the coin is obviously more unstable. It gets a little bit of stability, but eventually starts to wind down and rapidly bend over and start going for the surface there and eventually stopping. And as you give it more and more rotational motion, it's very clear that it gets more stable, sort of like a bicycle. If you lift it up and just kind of let it go, totally unstable. If you give it a little bit of rotation, very, very stable. And it's a lot more pronounced if you spin the coin. If I spin the coin, then it can stay up very, very long time. Now, even though it looks like kind of a solid sphere when it's spinning, if you spin it fast enough, it kind of looks like a solid sphere, right? In reality, there's only one contact point at the bottom. At any point in time when this thing is spinning around, there's only one point or very few points at the bottom there, if it's a little flat, where it's actually contacting the ground. But yet it's a lot more stable. In fact, so stable, if you're very quick, you can actually put several of these things in motion at the same time, and you can see that they're more or less stable. Why is a rotating object stable like that? Right? You've probably seen a gyroscope. One day I'll do a video just on a gyroscope, but a gyroscope is a spinning body that seems to be able to balance and resist the tendency to fall over just by nature of it spinning. What other examples have you seen in everyday life? I know that you've seen a frisbee, right? If you throw a frisbee, like, okay, if you don't spin the frisbee, if you just take it like this and just throw it, then it's just gonna tumble and do nothing. But if you give it some rotation as you throw it, then it is very stable in the air. Obviously it can go up and down, but very, very stable as you throw a frisbee, right? What are some other examples? I know that you've all seen ice skaters, even roller skaters, but ice skaters, you know, and or even ballerinas maybe. And so when an ice skater is rotating, he or she is very, very, very stable. And we've all seen when they put their arms very wide, they slow down. And then when they pull their arms in, they speed up. And it seems to be magical. Where is that coming from? Why is it when they pull their arms in, do they rotate faster? And why are they so stable, balancing on the tip of their ice skate there? It would seem to be very unstable, but just like the coin is more stable when it's rotating, the ice skater is also more stable when he or she is rotating. Now, there are other examples of stabilized systems when they're spinning. You may or may not know this, but when we launch satellites from like the space shuttle or other spacecraft into space, very, very often the satellite is rotated before it's deployed. And that is to give it some stability as it exits the cargo area of the spacecraft. If you don't spin it, then it can very easily start to tumble. But if you give it a little bit of rotation, then it's in a known orientation and it resists the tendency to kind of tumble out of control like that. So we very often do that. Often a lot of space probes that are sent to the deep solar system are also very slightly rotating as they travel out. And that's, again, to give them a little bit of stability in that way. You may have played with a yo-yo. You put it around your finger with the string and you fling it down, and it goes all the way down and then all the way back up. And then during its journey down and then back up again, it's rotating, and so it's very, very stable. Of course, you can knock it, it can get flipped over and stuff, but it's much more stable than if you just dropped it. If you drop a yo-yo, it might be tumbling on the way down, but when you fling it like this, you give it a lot of stability as it goes down and up. And the last example I'll give you is on the space station. There are gyroscopes called control moment gyroscopes on the space station, and they serve two purposes. They're these spinning gyros. Number one, they give the space station a lot of stability so that it resists the tendency to tumble and rotate. And secondly, by having these very, very high-speed rotating gyroscopes, if you move these gyroscopes with motors like that, then you can actually cause a reaction torque on the space station. And long story short, it's how they control the attitude of the space station, where it's pointing. So instead of thrusters on the space station, because it's so big, they have these gyroscopes which, by changing the rotation, spinning them up, spinning them down, changing their orientation, you can actually turn the entire space station structure. And we do similar things on cruise ships and boats and other things too there. Now, all of these systems, from the simplest thing, the spinning coins, all the way up to the space station, they basically operate on the same principle. And I'm going to get into a whole lot more detail in just a second. But the main idea is that just like when you throw something in a straight line, we say it has momentum. And you might have heard that there's something called the conservation of momentum. It's a law of the universe. As far as we can tell, there's no exceptions to it that we've ever done an experiment and seen an exception of it, right? Well, that's for a system moving in a straight line. There is an equivalent law called the law of conservation of angular momentum, and that applies to rotating systems. So when a system is rotating, it's said to have angular momentum. An angle comes in because it's rotating through an angle. Anything rotating goes through some sort of angle over some period of time, right? So linear momentum, we have the analog called angular momentum. So linear momentum, angular momentum, conservation of linear momentum, conservation of angular momentum. And all of these effects, like the stabilized coins, the stabilized frisbee, the stabilized spacecraft, they basically all boil down to the conservation of angular momentum. So I want to spend a little time giving you an intuitive understanding to what angular momentum is, how it differs from regular momentum, and why do things become a little more stable when they're rotating. So that's what we're going to do right now. All right, so to get started, what I'd like to do is review what regular momentum is. And so when things start rotating, you'll understand what angular momentum is, because the two concepts are very, very similar. And they're very, very closely related. All right, so we have this thing called momentum, right? And we use the letter P to represent momentum, and we say that the momentum of some particle or some body is equal to its mass times its velocity. Now, the velocity is a vector, which means we have an arrow over it, and the momentum is also a vector, which means we have an arrow over it. So what we do is we take the mass of a body, like in kilograms, let's say, multiply by the speed of the body, the velocity, which has some sort of direction, and then out comes this quantity, a new quantity called momentum. Right? So it depends not only how fast how something is moving, what direction and what speed it has, but also how much mass it has. Now, I want you to think about mass for a second. What is mass anyway? Well, none of us really know, all right? I mean, exactly the concept of mass, and I mean, we know it comes from atoms, but I'm talking about why mass has inertia. Those are deep, deep questions in the quantum mechanics. But what we do know is the more mass something has, the more inertia it has, which means the more it resists your pushing force. It resists changing its state of motion. If something is already at rest, like a bowling ball sitting here, and I push on it, I can move it, but it's going to be a little difficult to get it moving. If an object is already in motion, like in deep space going at some constant speed, then it's difficult to get it to change its direction. And the more mass, or its velocity, the more mass of an object, then the harder it is to get the motion to change. If you have a car, it's very hard to get a car moving. If you have a feather, it's very easy to get a feather moving. So mass is what we call the inertia of a substance. And it depends on the atoms that are in there and the type and the number of atoms, because atoms have mass down at the atomic level. But the more mass you have, the harder it is to get something to move and to get something to change its state of motion if it's already moving, okay? So that's momentum. And this is motion in a straight line, okay? Now we also have something called Newton's second law, right? You know, Newton has three famous laws of motion. The second law is the one you use all the time mathematically, and that's that the force that you apply to something that has some mass will cause it to accelerate. And notice that these are vectors also. When you see the arrows on top, don't worry about it too much, but what it basically means is that that quantity has a size, a magnitude, but also a direction. You know, acceleration and velocity have some direction, north or south or west or whatever. Same thing with forces and momentum. But the mass of an object has no arrow because it has no direction. This piece of paper has a certain amount of grams, but it has no direction associated with it. Pressure in a room has no direction. Temperature has no direction. So those are not vectors. But things like velocity, speed, and forces, they all have directions. So that's why we have the arrowheads on top. And that's going to become important later when we talk about spinning objects. Now this M here, it's very easy to overlook it, but I want you to, in your mind, begin to associate this M here with some quantity that represents the inertia of a substance. Now we call it the mass, but really it should be called the inertia, right? In fact, we're going to learn in just a second that when rotating systems come into play, we don't talk about the mass, we talk about the moment of inertia. We actually use the word inertia when we're talking about rotating systems, but for some reason when we talk about systems moving in a straight line, we just call it the mass. But in your mind, you need to be thinking, okay, that means inertia. The more mass something has, the harder it is to move, or to get moving, or to change its state of motion. That's all the mass really represents. All right? Now, we have this concept called momentum, and we know that this quantity called momentum it's conserved, the law of conservation of momentum. So in a collision, you can think of collision like two rocks hitting each other or two cars hitting each other. But anyway, before the collision, you know, if you have this thing moving this direction, and then you have some stationary thing like this, and they're going to collide, and they're going to be moving off, let's say, in different directions, like this, or I'm just drawing these arrows in random ways. But the point of it is not to put numbers to this problem. So this could be before and this could be after. But this particle has some momentum before the collision. Its mass times its velocity. And this particle has some momentum, its mass times its velocity. If it's not moving, then the velocity is zero and there's no momentum. And after the collision, this particle has some final momentum and this particle has some final momentum. And the momentum has not only a number, but it has a direction associated with it. What this means when we say that momentum is conserved is that before a collision and after collision, the total momentum of the two-particle system has to be the same. It has to be unchanged. So you can calculate how this thing is going to fly off, at what angle and all that stuff, based on knowing exactly what happens before. Because why? Because the momentum of the whole system here before and after has to be the same. The reason I'm bringing this up is because conservation of momentum, just like conservation of energy, is a fundamental law of our universe. If you want to know why momentum is conserved, then go get a PhD and write your dissertation on that, because that is something very, very deeply baked into our universe. It is something that we've never seen an exception to in any experiment. Conservation of momentum is always true. And we're going to talk in just a minute about conservation of angular momentum when something is spinning, and that is also always true, as far as we can tell. Right? Even at the quantum level, right? When you get down past, big objects like this and you start talking like single electrons, they have a quantity called angular momentum. Angular momentum goes all the way down into the quantum realm. It seems to be baked into our universe at a fundamental level. Okay? So, momentum is very fundamental. Newton's second law, very, very fundamental. All right? But spinning objects, as we talked about, have if they're not moving down in one direction or another, if they're just sitting in space spinning, they don't have any linear momentum because the velocity moving in a line is zero. But if they're rotating, they have angular momentum by virtue of their rotation. All right? And you might guess that as something is spinning faster, it has a higher angular momentum. And if something is spinning really, really, really slow, it has a lower angular momentum, and you would be right. So let's go over here and let's write down the concept of angular momentum. And I promise you, momentum, that I'll do my best to make it absolutely understandable by anybody there, anybody watching. All right, so just like you have P is equal to mv, we call angular momentum L. You have to pick some letter, so they don't want to pick A for other reasons. We use A for other stuff. We call it L. And I is right here. I'll talk about that in a second. And omega is here. Now this is like, whoa, you're like, what? This is so weird. So the angular momentum is called L instead of P for the linear momentum. But instead of mass, we have this I here, right? And instead of the velocity of the ball or whatever moving down in a line, we call it omega. So don't get too scared about this. This is called the angular momentum. I'm going to put angular momentum. This is the angle symbol, momentum, right? This thing is called the moment of inertia, right? And it replaces the concept of mass. Because as you might guess, it does depend on the mass of the object, but when something is rotating, it doesn't just depend on the mass, it depends on how the mass is distributed around the axis of rotation. I'm going to say that again. The moment of inertia doesn't just depend on how massive it is, like it does in regular momentum. It depends on how the mass is distributed about some axis of rotation. When you're rotating, you're always rotating about some axis. So the axis of rotation is critically important. It defines everything when you're talking about rotation. You have to know what axis you're rotating around. And instead of meters per second for velocity, this is called the angular speed. And so the units here you could use revolutions per second or whatever, but usually it's radians per second. And in math class, you learn about degrees and you learn about radians. Radians is just another angle measure around in a circle. So don't stress out too much about units. I don't want you to stress out about units. What I want you to see is the symmetry. Momentum is equal to something related to the mass times something related to the speed of rotation, because angular speed is representing how fast it's rotating in a circle, how many degrees per second, how many revolutions per second, how many radians per second. They're just different units to represent how fast something is rotating. So it's called an angular speed. So here's your speed. Here's your speed, here's your inertia term, we call it mass over here. Here's your inertia term here, we call it moment of inertia. And here's your momentum term, which is the same place over here. So these equations are identical in form, with one big difference. And the one big difference, or the two big differences, is that in regular momentum, the momentum P is just a vector that represents, which way it's going and how massive it is. But here, this angular momentum has to be in reference to some axis of rotation. So it's going to have a direction associated with it, and it's going to be pointing in along the axis of rotation, right? If the thing is spinning one way versus spinning another way, the angular momentum will be different, just because the axis of rotation is different. Okay, and also the second thing is this term here is not just a mass. It is something a little more complicated than the mass that I'm going to talk about in a second, but it relates to how many kilograms it is, but also how the kilograms are distributed in space, right, around the axis, basically. And I'll talk to you in just a second about this. First, let's do first things first. Let's talk about the angular momentum itself. Let's say that I have a spinning coin, just like I had in the video there. So I have a coin right here and I flick it and it's spinning like this. It's not rolling, it's spinning like this. So what you do is you, with your right hand, you put your fingers in the direction of the rotation. In this case, this would be like a coin literally spinning like this and resting on the ground right here. I guess I could put the ground, you know, underneath. It's going around and around like this, so I could do some rotation like that. And what you say is, if you put your right hand in the direction of rotation, your thumb points in the direction of the angular momentum. So here is the angular momentum vector. It points along the axis of rotation, because if you kind of extend the dotted line here, this is the axis of rotation. If the coin were spinning differently, the angular momentum would be along that axis of rotation, right? So this is called the right-hand rule. Put your fingers in that direction, thumb points in the direction of the angular momentum. Now, we can also talk about, instead of a spinning coin, we can talk about a rolling coin. Now remember, that one was literally rolling and kind of going in a direction as it was rolling here. So for this one, it's kind of hard to draw. So what I'm going to do is draw a three-dimensional axis here. So something like this. And then what I'll say is the coin is, you know, right here, let's say. And it's rolling this direction with some velocity. So it's going this way. But it's 3 dimensions, so it's kind of hard to describe. But basically, if you have it going like this, then you can represent the angular momentum. I guess I should have drawn it a little bit different. I'm kicking myself for that. Let me draw it a little bit different. We can say that it's like this. That's what I was trying to draw. Like this. And so if it's going this way, you could do the same thing. You could say, well, my right hand fingers are going this way, and so the thumb is pointing out of the board, and in this drawing, that means that the angular momentum is going to be like this. And what I'm trying to say is, if you literally have a coin and it's rolling this way, then my thumb is coming out of the board toward you, and that's this direction. So the angular momentum is coming out of the side. Here, the angular momentum is coming out of the top. So I'm just trying to get you used to the concept of, where does the angular momentum point? It just depends on the axis of rotation. You put your your fingers in the curling in that direction, and your thumb points in the direction of the angular momentum. All right, so that takes care of what is this. Now let's talk about this thing. This is called the moment of inertia. Let's see how much room I actually need. This thing is called the moment of inertia. So moment of inertia. Right? Let me illustrate that, right? If you can imagine a long tube out in front of myself here, and that tube, you don't really know what's inside of it, but I'm going to tell you that that tube is hollow, except for at the very center is like lead, right? And, you know, let's say 5 kilograms of lead, right? And then there's a second tube looking identical from the outside. Again, 5 kilograms of lead, but 2.5 kilograms on this end and 2.5 kilograms on this end. So the total mass of the tube is the same in both cases. It's just that in one case, the mass is concentrated in the center, and in the other case, the mass is concentrated at the ends. If I hand you each of these, one in each arm, and I tell you to try to spin it around like this, I think you can envision and kind of visualize that they would behave differently. They both have the same mass, but the distribution of the mass around the axis I'm trying to spin is different. So they're going to spin differently. They're going to feel differently. And so let me draw a picture of that. Let's say in one case, I give you a hollow tube with almost all of the mass concentrated in the center. And in the second case, I give you a sealed hollow tube where half of this mass, let's say that's about half of it, is over here. And the other half of the mass is basically over here. So it's completely hollow here, but only has the mass concentrated at the ends. This one is going to be very easy to rotate. I think you can visualize that. This one with a really, really heavy mass toward the end is going to be much, much, much harder to rotate. So this one is going to be easy. And this is going to be hard to rotate about this axis. Notice I have to define some axis, okay? And so what this means is that this is a low moment of inertia, I, and this is a high moment of inertia, I. I mean, it's the same concept as mass. If I tell you I have a low mass, what does it mean? Easy to move. Well, here I have a low moment of inertia, easy to move. Here I have a high moment of inertia, easy to move, but they're both, in this case, 5 kilograms, let's say. They have the same mass. So when things are rotating, it doesn't just depend on how massive it is. It depends on how the mass is distributed. If I have like a basketball that's completely hollow and the surface of the ball is like covered in lead so that all the mass is on the edge, and then I have another ball where it's like all the mass is concentrated in the center and almost nothing at the edge, those balls have the same mass, but they're going to rotate and feel different. And the more the mass is near the edge, the harder it is to get moving because it's far away from the axis of rotation, higher the moment of inertia. Now, this ties into torque and other things. I'm just going to give this to you for any of those that are interested. The moment of inertia, you don't need to know this for the rest of this. When you calculate it, is the sum over all of the particles, the atoms, let's call it, in the object. That's what this means. I'm just adding up from the first atom to the nth atom. There could be 100 trillion atoms in this whole thing. And it's going to be delta m sub I. That means the mass of each individual atom multiplied by the perpendicular distance squared from the axis of rotation. And when you add the product of this stuff up, then and you add it all up, that's the moment of inertia. So in this case, it's the same mass, but the masses are very, very close to the axis of rotation. R perpendicular is how far away it is from the axis of rotation. So you're going to add up very small distances here because almost all the mass is here. And so you're going to have a low moment of inertia. But here, you're adding up almost all the mass here. It's the same total mass when you add them all up, but all the mass is concentrated out here. So the distance to the rotation is very, very high. So when you add all this stuff, you're going to get a high moment of inertia. But notice the actual mass of the object is the same. It's just that the distribution is different, leading to a different moment of inertia. All right. Now, regular mass, m, when I push it, it's very hard to get moving, right? And that's what it means, it has a high inertia. High moment of inertia means it's hard to get rotating, right? Very low moment of inertia means it's very easy to rotate. That's basically what that is. Now, just like we have Newton's second law of motion, we have something else called kind of Newton's second law expressed in rotational terms. And before I go on, I'm just going to kind of summarize everything here because I think it's good to do that. So we have P is equal to mv for linear system, right? And we have F is equal to ma for Newton's second law. And then for a rotating system, we just said that the angular momentum, whoops, that marker's not doing good. Let's switch it out. Okay, angular momentum is equal to the moment of inertia times omega, and there is a F equals ma version when you rotate, and that's called the torque is equal to I alpha, right? So instead of F equals ma, you have torque is equal to I alpha. So the mass gets replaced with the moment of inertia. The acceleration in F equals ma gets replaced with the angular acceleration, how fast it's accelerating around the axis. And the force gets replaced by something called the torque. You can think of the torque being the force exerted around an axis. Think about a wrench. When you push on a wrench and you're always rotating it around some axis, and so you have a torque. A force is when we push in a straight line. A torque is when we kind of push along a circle or along a semicircular torque like this. All right? So I wanted to point that out because when we have linear momentum, we have angular momentum, which looks very similar with the mass replaced with the moment of inertia. We have Newton's second law replaced with this, where the mass is also replaced with the moment of inertia. The acceleration becomes the angular acceleration in radians per second squared, and the force becomes the torque, which is like an angular kind of force. So now let's start to get down to business here. Before we start talking about why the coins are stabilized, let's talk about something a little bit easier to understand before we get all the way there. talk about a ballerina. We've seen, or you can talk about a ballerina, or you can talk about an ice skater, right? Ice skater is spinning on the ice, arms outstretched, rotating very slow. Then they pull the arms in close to their body and spontaneously, almost like magic, they begin speeding up. Why does that happen? It's because of conservation of angular momentum. All right, so let's talk about that, right? Just like momentum is conserved, angular momentum is also conserved. So if you have a ballerina, right, like this, arms very, very far out, like this. That's the best I can do, right? Because the arms are very far around from the axis of rotation, which is spinning this direction, like this, right? Then we know that the moment of inertia is large. Why? Because the moment of inertia is not just the mass, it's how the mass is distributed. And when it's far away from the axis, the moment of inertia is big, just like it was for the rod. So it's a large moment of inertia. And then we say that the angular momentum of this ballerina is equal to I times omega. Because there is a very large moment of inertia, because I've spread my arms out here, then when I begin to spin with some angular speed like this, I multiply them together and I'm going to get some initial angular momentum. Now the way it works is, once a body has angular momentum, it's spinning, there's a law of conservation of angular momentum, and that just means that unless there's an outside force pushing on it somehow, then that angular momentum will always stay the same. Now the outside force could be if I go push on her, I could give her some more angular momentum or less. And when I say push on her, I mean push her in a rotating way. Really, it's called a torque, right? Or the ice skates are touching the ice. That's friction, and that is a kind of an external force slowing everything down. But I'm talking about if you were a ballerina in space, or a spacewalker, and a spacewalker like put their arms out like that, they would be, and you rotate them at some initial rate, they would have an initial angular momentum. And let's pretend there's absolutely no friction of any kind in space. So he would never slow down, ever, like forever. But if he or she brought their arms in, they would begin rotating faster. And then if you put them out again, you would rotate slower, and then faster, and then slower. And you could do that over and over forever because there would be no losses in space, right? Why is that? Well, let's draw a picture of the ballerina with the arms much closer to the body, like this. Now, if this is a very high moment of inertia, here, there's a very low moment of inertia. And because the angular momentum is I times the angular speed there, what I've done is I started out with some initial angular momentum here, right? And I had a very large moment of inertia. And what happened is, there's no external forces we're pretending. But I instantaneously, by pulling my arms in, I lower this. I make this low. So lower. So in order to give me the same angular momentum I started with, because remember, it has to be conserved, that means it can't change, then the only way it can happen is if the angular rotation gets higher, which means they begin spinning faster. So the reason why the ballerina begins spinning, or the ice skater begins spinning faster, is because when they were outstretched, they gave themselves some initial angular momentum. They start spinning on the ice, right? And their moment of inertia was big. So their angular rotation rate was whatever it was. But there's no external forces anywhere else other than friction with the ice, which is small. So when they bring their arms in, they immediately make their moment of inertia really, really small. And that makes them speed up really, really fast, making the angular rotation rate faster. Why? Because the momentum before and after this happens has to be the same. Let's say the angular momentum was 5. And by the way, which direction is the angular momentum pointing? If we're rotating this way, the right-hand rule means angular momentum is here. And so after, the angular momentum has to be the same direction and the same length. And the only way that it can be the same direction and the same length, if I change this one and make it smaller by pulling my arms in, then the rotation rate has to get bigger, has to speed up. And that is exactly why that happens. So that's the concept of conservation of angular momentum. And the same thing happens to a diver. You see a diver jumping off a platform. And when their body is very outstretched, they're rotating very slow. But when they tuck, then they begin rotating really fast. And when they stretch out again, it's very slow, because the angular momentum has to be the same. When they go big and small, they're changing their moment of inertia. And so the only other variable there is the rotation rate, and that has to change according to the angular momentum. All right, so here I want to do my best to describe why the spinning coin that we did is pretty stable, relatively stable, until friction with the table slows it down. And it's a little hard to draw, but I think I can do a good job of it. I think you can get a good understanding of it. The fundamental thing you have to understand, the most important thing, is that the angular momentum is a vector. It doesn't just have a number like 5 or 10, it has a number and a direction. In this case, the angular momentum is like, I don't know, 10, whatever unit you're working in, but it's pointed up. And so after I do this, it has to be 10 and pointed up, right? But it has a direction associated with it, is what I'm trying to say. And before and after whatever event, the angular momentum has to be the same as it was before and pointed in the same direction. That's important. So it's not just a number, it has to still be pointed in the same direction. So let's do this by drawing a couple of different pictures. Let's say I'm rolling the coin, and this is going to be a top view, right? Top view looking down. So what I have is my coin here, and then what we're going to do actually, because it's a little easier to understand it, instead of talking about the spinning coin when I use my finger and I thump it, let's talk about the rolling coin. That's just a little bit easier to visualize, but the same concept will apply to the spinning coin. When you roll the coin, it's moving in a direction and it's also rotating, so it has angular momentum because of the rotation. So if you envision it going and moving this direction, like some velocity, like this, then it has to be going like this, and from the right-hand rule, it would be rolling this way. My thumb would be pointing to the left. That means the angular momentum would be coming straight to the left out of the side. So it has a length, a number, and it has a direction. And when I let go of it, it has this angular momentum. And the angular momentum is never, ever going to change unless there's an outside force or torque acting on it. Yeah, basically forever. Now in reality, the coin is rolling on a surface and the surface has friction, so that's slowing it down. So eventually it's going to slow down and fall over. But if there was no friction at all, it would literally have the same angular momentum forever. It would have to, because it's a law of the universe that angular momentum is always conserved. So let's say though that in our real universe, there is a wind or something that causes it to slightly become unbalanced and gravity begins to pull it down over. Let's just say, for instance, that gravity begins to pull it one way. How will the system react? So let's draw another picture just like a second later. It's still rolling that way, but at this moment in time, it begins to fall to the right. Right? It begins to fall to the right. Now, it still has that angular momentum pointed to the left, right? But when I say fall to the right, this thing is rolling that way. What I'm saying is it's trying to topple over like this. And because it's trying to topple over, what will that angular momentum look like? If you have something here that's trying to fall over, it's trying to rotate this way, which means if I use my fingers like this, if it's trying to fall over, then it's trying to do this, then my thumb is going to point in the angular momentum direction like this. And I'll put another L here. So it's got some angular momentum from the rolling, but because it's trying to fall over, microscopically, I'm talking about, microscopically begin to fall over, has a little bit of angular momentum in this direction. All right, so what is the total angular momentum of this coin now? Well, I have a vector from the one it had initially, and I have another vector very momentarily, before the system has time to react, if you want to think of it that way, pointed in another direction. They're both vectors, and you can add the vectors, okay? Now, adding vectors is not exactly the same as adding numbers. You don't just add the numbers, you have to take into account the direction of the arrows too. So here is a third situation when we add these things together. And you can think of them almost as forces, but just think of them as an arrow here and an arrow here. So when you split if they were exactly the same length, then it would be something like this, okay? So of course, in real life, it's not gonna be this exaggerated, but because I'm gonna draw them roughly the same length, and so I'm gonna say, it splits the difference, and so the new resultant vector is something like this. Okay? Now this angular momentum is pointed in a different direction as this one, and it also has a different length too. But the thing I want you to point out or understand is that it's pointed differently than before. You see, with the ballerina from before, when he or she pulled the arms in, the angular momentum was still pointed up, so it only affected the speed, right? But here, whenever gravity tried to pull the coin over a little bit, just like if you don't roll it at all, if you just let it go, it eventually falls over, right? Well, when you're rolling it, gravity tries to pull it over, and in doing so, it changes the angular momentum from its starting direction to a new direction. And I just told you that the system obeys the law of conservation of angular momentum. And that means that the system, actually, let me erase this. The system will attempt to compensate for this change in momentum to bring it back to where it was originally. And what it's going to do is the coin is going to begin to turn to the left in order to keep this angular momentum in the same direction as it was initially. So think about what you have here. So this is a turn to the left. You see what I'm saying here is originally the coin is rolling, okay? Gravity randomly begins to make it fall to the right, a microscopic amount. And in doing so, it gives it a little bit of angular momentum, which adds with the original, which gives a tiny new resultant in a different direction here. The system will react so that the coin will turn this way to bring the momentum back in line with where it is initially, because there is a law of conservation of angular momentum. The system will always react to be able to keep the direction of the momentum it had and the magnitude of the angular momentum it had, because it can't change ever, right? Unless an outside force acts on it. In this case, gravity is acting on it. And so it's trying to compensate for that by bringing it back. And the way it brings it back is by turning a little bit to the left. So when gravity attempted to make the coin fall to the right, the system reacted by bringing and turning the coin to the left, which counteracts its tendency to fall to the right. Let me say that again. When randomly gravity tries to pull it down one way, a torque is generated to make it turn the opposite way in order to bring the momentum back to where it should be. So it's unchanged, right? And that process, that turn, that counteracting turn, tends to undo the initial fall to the right. If the coin initially was trying to fall to the left, then the coin, everything will be opposite, and it would begin to turn right to counteract that. So when you roll a coin, microscopically it's trying to turn, but the system is microscopically bringing it back in alignment, and so it's rolling in a much more stable configuration. The same thing is happening with these rotating satellites, with the Frisbee, or whatever. The reason why they're stable is because if any outside force attempts to move them and change their angular momentum vector, then a torque is generated, which pulls it back and brings the momentum back so that it's unchanged from its original state. And the same thing happens with the spinning coins. When I'm thumping them and I'm spinning them like that, the angular momentum is pointed up because your fingers in the direction of the rotation, angular momentum would be pointed up. If gravity attempts to bring it left or right, notice my thumb is pointed in the direction of the angular momentum. If it tries to fall over this way, then a torque will be generated, which will bring it back to the vertical position there. And eventually the thing loses speed due to friction, and so the effect isn't as pronounced, because as it loses speed, its angular momentum goes down, 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 and then it can't maintain its state as well. And the same thing happens with a gyroscope. When you pull the string on a gyroscope and it begins spinning very, very fast, and you balance it, we think that it should just fall over. But what actually happens is as soon as it tries to fall, it begins to kind of do this precession thing. And it's because as it falls over, it's trying to compensate and keep its angular momentum vector the same as it was in its initial state. Eventually, due to friction, the angular momentum decreases to the point where this process can't happen anymore, and then the thing just falls over eventually when it runs out of angular momentum. Everything in the real world, unless you're in deep space, is going to have friction. It's going to slow down. All right, so that is why something as simple as coins rolling and spinning are so much stable. That is why a yo-yo is stable. That is why a Frisbee is stable. That is why the control gyroscopes in the space station make the space station stable, because of the conservation of angular momentum. And it tries to remain unchanged before and after some event. And it will try to counteract in such a way to keep the momentum vector the same size and the same direction as it was initially. Now, the last thing I'm going to leave you with is, I think this is the best way to think about it. And I think this is the way all students are introduced to it. But There is a little bit of uncomfort there because I'm using words like it generates a torque to counteract it and it wants to stay up. I'm using these words like it has a mind. There's no mind here, okay? It's just a counteractive thing happening to keep the momentum in the same direction initially. But there are alternative descriptions down here. I mean, this coin rolling is comprised of trillions and trillions and trillions of atoms. So if you really wanted to model this coin properly, you could break it into trillions of atoms, and they're each going around some central axis of rotation. And you could then model the force of gravity trying to pull it over, affecting some atoms differently than others, and really go through all the forces, and you would arrive at the reason why this counteracting of the torques actually happens, and essentially how the momentum vector tries to stay upright. You can do the math of why a gyroscope stays upright there, and it gets pretty complicated pretty fast. I didn't go that direction because I wanted you to understand it from the point of view of conservation of angular momentum, because at the end of the day, even if you understand it at the atomic level, why it does what it does, at the end of the day, it all boils down to it's going to react in such a way that the angular momentum is unchanged. And at the end of the day, that is what is going to help you to solve problems, to understand things. Going at a deeper level is never a bad idea and always good for deeper understanding. But I think at this level, the best description is just to say that rotating objects have an angular momentum vector, just like objects moving in a straight line have a linear momentum vector. And just like there is a law of conservation of linear momentum, you could ask, where does that come from, right? Then there is an equivalent law of conservation of angular momentum, because at the end of the day, when things are rotating, they all consist of atoms moving. When you zoom microscopically in, even though it's rotating, if you go small enough, every little atom is moving tiny in a straight line for a small fraction of time until it begins to rotate around. So linear momentum and angular momentum are kind of connected at the microscopic level when you zoom in tight enough, right? And that is why these equations are so similar, right? Momentum, angular momentum. It's Newton's second law for rotating objects. All right, I probably went too far into this, to be honest with you. I could have just said, hey, spinning coins, it makes it stable because reasons, But I wanted to get into a little bit more detail and show you that I think, even though there was a little bit of math in this, I think that it's not too hard for someone to understand. Spinning objects have something called an angular momentum vector, has a direction and a magnitude. And anything that tries to upset that, the system is going to react in such a way to try to maintain the original angular momentum it had, because that is a law of the universe. It applies to particles, applies to atoms, applies to planets, applies to galaxies. Heck, we're even seeing in deep space it applies to stars. Did you know that most stars rotate, right? They actually have a rotation period. Our sun rotates over a period of several weeks, right? And as a star runs out of fuel, then it begins to collapse on itself because there's not as much internal pressure pushing out and gravity begins to contract it. So it's just like the ballerina. What do you think is going to happen? If it's rotating and the star begins to physically shrink, like, down to, a few thousand kilometers or whatever it is, becomes like a neutron star, then this thing is going to start rotating really fast. And we see that in the sky. We see pulsars and other really fast rotating stars because they were originally much larger stars that collapsed. And because of conservation of angular momentum, they began rotating much faster once they collapsed, just like the ballerina. I hope you've enjoyed this. Or keep saying the ballerina. The ice skater is really what I'm trying to say. I hope you've enjoyed this. Please drop me a line, let me know what you think. And don't forget, always stay curious. Learn anything at mathandscience.com.